Welcome back. Episode 6 gave us the chain rule, and we used it to differentiate e to the 3x on faith, assuming that the derivative of e to the x is e to the x itself. Episode 7 finished off the trig functions. Today we pay the second debt. We're going to find a single function that equals its own derivative. We're going to discover that the number e, the constant, whose value is about 2.718, is exactly the base that makes this work, and we'll see what e really is, not as a magic constant printed on the back of a calculator, but as a limit you can compute by hand. From there, we'll get the derivative of a to the x for any positive base, the derivative of the natural log of x via implicit differentiation, the derivative of log base a of x via change of base, and the technique called logarithmic differentiation that handles functions with the variable in both the base and the exponent. By the end of the episode, we'll also have the power rule for any real exponent, not just integers, closing a loop that started in episode 4, 3 worked examples, a short history of e, and one of the most beautiful identities in all of mathematics. Let's go. Where does the number e come from? The cleanest answer is compound interest, which is exactly the setting where Jacob Bernoulli first noticed it in 1683. Suppose you invest $1 at a 100% annual interest rate, and the bank compounds your interest n times per year. At the end of 1 year, your account holds the quantity 1 plus 1 over n raised to the nth power. If they compound annually, n equals 1, and you end with $2. If they compound semi-annually, n equals 2, and you get 1 plus a half squared, which is $2.25. Monthly, about $2.61. Daily, about $2.71.4. Bernoulli noticed something. As n keeps increasing, the value doesn't shoot off to infinity, it converges. The limit is a specific number, about 2.718, which Euler later named e, so e is defined as the limit of 1 plus 1 over n, all to the nth power as n goes to infinity. Continuous compounding at 100% for 1 year yields e dollars. That's where the constant lives in the world. Here's the conceptual reason that one base out of all the positive numbers is special. Pick any base a, could be 2, could be 3, could be 10, and look at the graph of a to the x. Every such graph passes through the point 0, 1 because a to the 0 is 1. But the slope of the curve at that point depends on a. For a equals 2, the slope at 0 is about 0.693. For a equals 3, the slope at 0 is about 1.099. As it sweeps from 2 up to 3, the slope sweeps from about 0.69 up through 1 and onto 1.1. By the intermediate value theorem, somewhere in that interval there is a base for which the slope at 0 equals exactly 1. That base, by definition, is e. So e is the unique positive real number whose exponential e to the x has slope 1 at the origin. It's exactly that choice of base that makes the derivative formula come out as clean as possible, with no leftover scaling constant. That's the reason calculus prefers e over every other base. Now derive it. Apply the limit definition of the derivative to e to the x. The derivative is the limit as h goes to 0 of e to the x plus h minus e to the x, all over h. Use the exponential identity, e to the x plus h equals e to the x times e to the h. Substitute and factor out e to the x, which is a constant with respect to h. The result is e to the x times the limit as h goes to 0 of e to the h minus 1 over h. Now look at that remaining limit. It's exactly the slope of e to the x at the origin, the quantity L of e from the previous slide. And we defined e to be the base that makes that slope equal 1, so the remaining limit equals 1. Multiply e to the x by 1, and the answer is e to the x. The derivative of e to the x is e to the x. The function equals its own derivative. Up to a constant multiple, e to the x is the unique fixed point of the differentiation operator, and every linear differential equation in physics has that fact hidden inside it. Look at the picture. The orange curve is y equals e to the x. At x equals -1, the height of the curve is 1 over e, about 0.368, and if you draw the tangent line there and measure its slope, you also get 1 over e. At x equals 0, the height is 1, and the slope is 1. At x equals 1, the height is e, about 2.718, and the slope is also e. At every single point on this curve, the slope of the tangent line is exactly equal to the height of the curve. That's the geometric meaning of the identity. The derivative of e to the x equals e to the x. The growth rate of the function at any moment equals its current value. A population that grows in proportion to its size, bacteria in a petri dish, say, follows exactly this curve because the rate of new births is proportional to the number of organisms currently alive. That's the slope equals height property, drawn. Now generalize. What is the derivative of a to the x for any positive base a, not just a equals e? Two-step trick. Step 1. Rewrite the base using the identity a equals e to the natural log of a. That's just the inverse function statement that exponential and log undo each other. So a to the x becomes e to the natural log of a raised to the x, which is e to the x times the natural log of a. Step 2, chain rule on e to the x times the natural log of a. The outer function is the exponential, whose derivative we just proved is itself. The inner function is x times the natural log of a, where the natural log of a is just a constant, a number. So its derivative is the natural log of a. Chain rule, outer derivative at the inner times inner derivative. That's e to the x times the natural log of a times the natural log of a. Convert back, e to the x times the natural log of a is just a to the x. So the final answer is a to the x times the natural log of a. Notice what just happened. The natural log appeared as a multiplicative penalty for using the wrong base. If you pick a equals e, then the natural log of e is 1, and the penalty vanishes. Every other base picks up its own personal constant, the natural log of 2, the natural log of 3, the natural log of 10, that hangs off every derivative forever. That's the second reason calculus prefers e. And now the natural log. Let y equal the natural log of x. By the very definition of the natural log as the inverse of e to the x, this means e to the y equals x. We want the derivative of y with respect to x. Differentiate both sides of e to the y equals x with respect to x. The right side is easy. Derivative of x is 1. The left side requires the chain rule, because y itself depends on x. The outer derivative of e to the y is e to the y. Exponential is its own derivative. And the inner derivative is the derivative of y with respect to x, because we're differentiating y with respect to x. So the left side becomes e to the y times the derivative of y with respect to x. The equation reads e to the y times the derivative of y with respect to x equals 1. Solve for the derivative of y with respect to x, it's 1 over e to the y. And e to the y is just x by the definition of y. So the derivative of y with respect to x is 1 over x. The derivative of the natural log of x is 1 over x. That's the second great result of today. Quick note on technique. We just did implicit differentiation, differentiating an equation in which y is not isolated, treating y as a hidden function of x, and using the chain rule on every y term. That's the entire content of episode 9, which we'll do properly next time. Here it's just one application, enough to get the log derivative out. One more derivative to complete the table. The logarithm to a general base a. Use change of base. Log base a of x equals the natural log of x divided by the natural log of a. The denominator, the natural log of a, is just a constant, a number, so it pulls out of the derivative as a multiplicative constant. The derivative of log base a of x is 1 over the natural log of a times the derivative of the natural log of x, which is 1 over x. Multiply 1 over x times the natural log of a. There it is again. The same natural log of a penalty that appeared on the derivative of a to the x shows up on the derivative of log base a of x. Set a equals e, and the penalty disappears. The natural log of e is 1, so the derivative of the natural log of x is 1 over x with no leftover factor. Every other base, common log base 10, binary log base 2, picks up its personal natural log of a in the denominator. The full logarithm, exponential table, reduces to 2 clean lines if you stick with base e, and 4 messier lines if you don't. Before our showpiece example, let's make the technique explicit. Logarithmic differentiation. Suppose y equals some complicated function f of x, a product of many factors, a quotient with messy pieces, or worst of all, an expression with x in both the base and the exponent. The recipe is 4 steps. Step 1, take the natural log of both sides. The natural log of y equals the natural log of f of x. Step 2, simplify the right side using the properties of logarithms. The natural log of a product becomes a sum of natural logs. The natural log of a quotient becomes a difference. And, this is the crucial move, the natural log of a to the b becomes b times the natural log of a. That property pulls exponents down into multiplicative factors, which are much easier to differentiate than exponentials. Step 3, differentiate both sides implicitly with respect to x. The left side, by the chain rule, becomes 1 over y times the derivative of y with respect to x. The right side is whatever it is. Step 4, multiply both sides by y to isolate the derivative of y with respect to x, then substitute y equals f of x back. You're done. Products become sums, exponents become multipliers, and the whole calculation simplifies. Let's see it. First worked example. Differentiate e to the 2x squared. The outer function is the exponential, the inner function is 2x squared. Chain rule. Outer derivative, e to the u, is its own derivative. Evaluated at the inner, that gives e to the 2x squared. Inner derivative, derivative of 2x squared, is 4x. By the constant multiple and power rules, multiply. The product is 4x times e to the 2x squared, which by convention we write with the polynomial factor in front. Notice the structure once more. The exponential reproduces itself unchanged, and the inner derivative, 4x times, tags along as a multiplicative factor. This is the same pattern we saw with e to the 3x in episode 6, just with a more complicated inner. The exponential signature, outer always reproduces, inner pulls out as a factor. That's the shape every e to a function calculation takes. Second worked example. Differentiate the natural log of x squared plus 1. The outer function is the natural log, the inner function is x squared plus 1. Chain rule. Outer derivative, the derivative of the natural log of u is 1 over u, evaluated at the inner, that's 1 over x squared plus 1. Inner derivative, derivative of x squared plus 1 is 2x, by the power and constant rules. Multiply. The product is 2x divided by x squared plus 1. Done. A small domain note. We don't need absolute value bars on the argument here because x squared plus 1 is positive for every real x. It's never 0, never negative. So the natural log of x squared plus 1 is defined and smooth on all of the real line, no restrictions needed. This is the textbook chain rule, with log pattern, and you'll see variations of it constantly. Logs love to wrap themselves around things that are always positive. Polynomials with no real roots, like x squared plus 1, or x squared plus a squared, or 1 plus the exponential of something. The watch for them. Now the showpiece. Differentiate x to the x for positive x. Look at this function carefully. The base is x, the variable. The exponent is also x, the variable. This is not a power function. The power rule needs a constant exponent. It is not an exponential function. The exponential rule needs a constant base. Neither rule applies on its own. We need logarithmic differentiation. Take the natural log of both sides. The natural log of y equals the natural log of x to the x. Use the log identity that pulls exponents down. The natural log of a to the b equals b times the natural log of a. So the natural log of x to the x becomes x times the natural log of x. Excellent. The variable has come down out of the exponent and now sits as a multiplicative factor. Differentiate both sides. Left side, by the chain rule, the derivative of the natural log of y with respect to x is 1 over y times the derivative of y with respect to x. Right side, product rule on x times the natural log of x. Derivative of x is 1 times the natural log of x, plus x times the derivative of the natural log of x, which is 1 over x. The x times 1 over x simplifies to 1, so the right side becomes the natural log of x plus 1. Set the two sides equal, 1 over y, times the derivative of y with respect to x equals the natural log of x plus 1. Multiply both sides by y and substitute y equals x to the x. The derivative of x to the x is x to the x times the quantity the natural log of x plus 1. That's the answer. A function with the variable in both the base and the exponent, and we cracked it in 5 lines, with no special x to the x rule, no lookup table. The technique generalizes. Anything of the form f of x raised to the g of x falls to logarithmic differentiation in exactly the same way. And now the loop closes. Back in episode 4, we proved the power rule. Derivative of x to the n is n times x to the n minus 1 for positive integer exponents using the binomial theorem. In episode 5 and 6, we extended it to negative integers and previewed the real exponent case. Today, we finish it for every real number. Pick any real exponent alpha. Could be the square root of 2, could be pi, could be minus 7/3. Rewrite x to the alpha using the identity x equals e to the natural log of x. Then x to the alpha equals e to the natural log of x raised to the alpha, which is e to the alpha times the natural log of x. Now chain rule. Outer is the exponential, inner is alpha times the natural log of x. Outer derivative, e to the alpha times the natural log of x, which is just x to the alpha back. Inner derivative, alpha times the derivative of the natural log of x, which is alpha over x. Multiply. The product is x to the alpha times alpha over x. Combine the powers of x to the alpha divided by x to the 1 is x to the alpha minus 1, so the derivative is alpha times x to the alpha minus 1. The power rule for every real exponent in 3 lines. The fact we've been using freely since episode 4 for fractional and irrational exponents is now rigorously proved. Loop closed. A short history. John Napier, a Scottish mathematician, published the first tables of logarithms in 1614. His goal was practical: multiplication is hard, addition is easy, and logarithms turn one into the other. Kepler and other 17th century astronomers used Napier's tables to do multiplications that would have been impossible by hand. Constants closely related to 1 over e appeared in Napier's work, but Napier himself never isolated e as a number worth naming. That happened 69 years later. Jacob Bernoulli, working in Basel in 1683 on compound interest, noticed that 1 plus 1 over n all to the n converges as n grows to a specific number near 2.718. First published appearance of EA. The naming and the modern theory came from Leonhard Euler. In a 1731 letter to Goldbach, Euler used the symbol e for the first time. Then, in his 1748 book Introductio in Analysum Infinitorum, Euler laid out the modern theory of e to the x and the natural log of x, the Taylor series for e to the x, and his most famous identity, e to the I pi, plus 1 equals 0. 5 fundamental constants and 5 symbols. 3 centuries, Napier, Bernoulli, Euler, collaborating on every line of today's table. Why e to the x and the natural log of x are everywhere. 5 reasons, picked from different corners of the mathematical universe. First, differential equations. The equation y prime equals y, the function whose rate of change is itself, has exactly one family of solutions, y equals c times e to the x. Every linear constant coefficient differential equation in physics and engineering is built from exponentials, because e to the x is the unique fixed point of the differentiation operator. Second, probability. The bell curve density, e to the minus x squared over 2, is the only probability density on the real line invariant under Fourier transform, a coincidence that drives the central limit theorem and most of modern statistics. Third, number theory. The prime counting function, pi of x, the number of primes less than x, grows asymptotically like x divided by the natural log of x. The prime number theorem, proved in 1896, has the natural logarithm at its heart. Fourth, finance. Continuous compounding is exactly the Bernoulli limit we use to define E, applied with real money. The Black-Scholes formula for option pricing is built from exponentials. Every interest rate model the financial world uses runs on e to the x. Fifth, physics. Radioactive decay, n of t equals n naught times e to the minus lambda t. Capacitor discharge, v of t equals v naught times e to the minus t over rc. Newton's law of cooling. And in quantum mechanics, the time evolution of any state is multiplication by e to the minus I times h times t over h bar. Every one of these starts here, with the derivative of e to the x equal to e to the x. Where we landed today. 7 results, 2 of them long promised. First, the number e, defined as the limit of 1 plus 1 over n, all to the n, as n goes to infinity, about 2.718. It's the unique base whose exponential has slope 1 at the origin. Second, the derivative of e to the x is e to the x itself. The slope of the curve at every point equals its height. Third, for any positive base a, the derivative of a to the x is a to the x times the natural log of a, obtained by rewriting a to the x as e to the x times the natural log of a and chain ruling. Fourth, the derivative of the natural log of x is 1 over x, obtained by implicit differentiation on the identity e to the y equals x, a one-line preview of next episode's main technique. Fifth, the derivative of log base a of x is 1 over x times the natural log of a via change of face. Sixth, logarithmic differentiation as a technique. Take logs, simplify, differentiate implicitly, solve, apply to x to the x, whose derivative came out to x to the x times the quantity the natural log of x plus 1. And seventh, the power rule for every real exponent, derivative of x to the alpha is alpha times x to the alpha minus 1, closing the loop that started in episode 4 with positive integers and ran through episode 5 for negative integers. A short history, Napier 1614, Bernoulli 1683, Euler 1748. 3 centuries of work compressed into one table. Next time, implicit differentiation in full, when the equation relating x and y won't let you isolate y on one side, and related rates, where multiple variables change together and the chain rule ties them. See you there. E to the x is the function whose rate of change is its own height, the cleanest feedback loop in calculus. The way this channel grows is the same feedback loop. 1 like compounds into 1 recommendation, 1 share compounds into 10 new viewers. Thanks for closing the loop with us. If you got something out of this, please like the video, drop a comment with what clicked for you or what didn't, and subscribe for more educational videos. Every like, comment, and share helps push this work to more learners, which is what this channel is really about. Thanks for watching. See you in the next one.